So hey and welcome back to F110 Autonomous Racing. In this video, I'm going to walk you through the first assignment of this course. So we have, learned just about everything that we need to know to now attempt building an autonomous swimming turtle in our Turtlesim ocean. And so this is the first assignment of this course. You have roughly just a little less than 2 weeks from when this assignment is out, which is today, to it's when it's due, which is on Thursday, 25th of March, by the end of the day. And this is a firm deadline. We won't have any extensions. I do think having roughly 2 weeks is enough time to cover everything that you need to do and submit for this assignment. So this video is not a lab session, it's not a lecture, but this is really walking you through what you are required to submit for this assignment and what are the different subproblems. So we have to be very sort of specific in terms of what you have to do, and then I'll also walk you through how you have to submit the assignment, since this is a remote online class this semester. So let's jump into what is it that has to be done for this assignment. So it's a very exciting assignment because you will create essentially a self-swimming or self-driving or really like an autonomous turtle using the ROS Turtlesim simulator that we have been using all along in nearly every lab session that we did together. So overall, the goal of the assignment is to really evaluate your understanding of the basics of ROS in terms of how to write new ROS nodes, how to publish, how to subscribe, use ROS messages and topics and things like that. You'll also use some ROS services that Turtlesim makes available, and then you will also be working with some launch files that we covered just last week. So in a nutshell, this is evaluating and building upon everything that we've learned so far. So it should be a fairly straightforward exercise if you have been following along. And a few things to get started with this assignment. So far we have been using our beginner tutorials package for all the lab sessions. If you go to this GitHub link, which is included on the slide, I have added and pushed another package called AutoTurtle. And so what you should do even before you begin attempting any of the problems that we'll discuss in just a second, you need to run a git pull to get a copy of this latest version of this repository, which will contain the AutoTurtle package. And just like, we copied the beginner tutorials from the GitHub to our Catkin workspace, and then we were using that for all our lab sessions, you have to do something similar. You can either copy the AutoTurtle package from your local Git repo into the source subdirectory of your Catkin workspace, or there's another option where you can symbolically link the AutoTurtle package from your Git repo to the subdirectory in your Catkin workspace, and the command for that is shown here. Symbolic linking and copying are sometimes used interchangeably, but there's a subtle difference. And if you've been using a Linux, then I'm hoping that you've seen symbolic linking before. But even if you don't know what this is, or you don't want to bother linking the AutoTurtle directory with the Catkin workspace, you can simply just copy paste, just like we did with our beginner tutorial. So as long as your Catkin workspace source subdirectory, so this part right here, this contains the AutoTurtle package, what you should then do is run catkin make from the root folder to build this new package. And this package contains some template code that you will use for the assignment. And so then inside that package, there's a folder, I believe, called scripts, which contains a node called turtlesimmove.python. And when you build, by the way, the AutoTurtle package for the first time, I also advise you to make sure that this Python file is executable. So you can do a chmod and give it executable privileges, just to be sure. So usually it will be executable, but if you run into problems, that would be one thing I would check. So the template code is called turtlesim_move.python, and a very good way to check that you have successfully taken this new code in AutoTurtle and you are ready to now start attempting the assignment is to launch raw score, launch a Turtlesim node, and then launch this and run this node. I keep saying launch, but I actually mean run this node called turtlesim underscore move.python. So you should just do ROS run, name of the package is autoturtle, and turtlesim underscore move.python. And then what you should see is that the turtle will automatically just move along its original heading, and it'll continue moving until it sort of crashes into the edge of the ocean. And if that happens, then everything is in good shape. You have successfully copied the contents and run catkin make, and you're now ready to write your own nodes building upon this template that is provided. So it's very important that this works for you, and if this doesn't work, then something is wrong either in the catkin build process or your workspace is broken, and you may have to like repeat all of this from scratch, where you delete your workspace and copy the entire Git repo and build it and so on and so forth. So let us know on Piazza if you run into problems with that. But this is the baseline sanity check that the code that we have pushed is going to work for your virtual machine. Okay, so assuming everything goes as planned, let's jump into the first problem that you have to solve. And really, this problem is one of Turtlesim swim school. So we are teaching our turtle to start autonomously swimming in the ocean. And this has many sub-problems, and incrementally they will become a little bit difficult. So let's look at the first problem, which is problem 1A. By the way, the name of the problem, which is the title of the slide, should be exactly the name of the file in which you write the ROS node for this problem. So that's true for all other problems as well. So for example, when we said problem 1A is swim underscore school.python, that's exactly what we are looking for in the submission, that you have submitted a file called swim underscore school.python, and that's what our kind of checker will run. So it's very important you respect the exact name, including the case sensitive parts of it when you submit and write your node. So what is swimschool.py? The problem 1A is using the template code that we have provided. You need to write a new ROS node with this name called swim underscore school.python. And you can build upon the template code or copy it and change it as you see fit. But you need to make the following modifications, right? So in the demo of this problem, what we are looking for is that when you run the command ROS run autoturtle swim school.python, essentially when you run this node that we are asking you to write, there's a prompt which appears on the terminal, which is asking the user to input a linear velocity in a particular range. So in this case, the range it should be between 2 and 6, but this is not always an integer. Like I could input 2.3 or 3.6 or whatever. Let's say up to one place of decimal, and it's not specified, but I just realized that we should probably specify that. So the user can input a linear velocity in this range, and similarly, the user can input an angular z velocity in the range 1 to 3, again with floating points allowed. And when they hit return after they input these numbers, what should happen is that the turtle should swim in a figure 8 shape using the linear and the angular velocity rates as specified by the user. Okay, so how that figure 8 is drawn or how the turtle swims is really where you have to write your ROS node. Okay, so let me maybe show you an example of what this looks like. So I have Turtlesim running, and what we expect the demo to look like is that we run this node called swimschool.python. It's asking for some linear velocity and angular velocity, and when you hit return, you can see how the turtle has started swimming, and it's drawing this figure 8 shape as it continues to swim in the ocean. So make sure that over time, your figure 8 is not drifting visibly, right? So there may be some drift because of how publishing and subscribing works. But it should be a pretty concise and figure eight, and that's really what we are looking for as part of the first problem. So I'm already showing you the solution where you have to write the ROS node to get us there. So hopefully that's clear enough, and it's really building upon things that we've done before. We already know how to make the turtle go around in a circle. Okay, so let's move on to problem 1b. This is building upon the previous problem. So it's similar to what you have done in 1a, except that now we are asking you to add some randomization to your code. So this problem requires you to write a new node called random swim school .python. So you have to write this exact node with this name. And here the demonstration is that upon running this node, a random figure eight is drawn, right? So in the previous problem, you were asking the user to input stuff, but here a random figure eight is drawn, and I want to go over all different randomizations that you have to include. So firstly, you have to choose a random linear velocity and a random angular velocity, and you can use the same ranges as the previous problem 1a to make this choice. But it should be randomized, so don't like hard code some values in your code which lead to good circles. And then every time this node is run, a random value is chosen. And in addition, not only is the linear and the angular velocity random, the center or the starting point of the figure eight itself is at a random position in the entire ocean, right? So because it is random, it could spawn randomly even close to the edges or somewhere near. That's all fine if during the swim, if the turtle sort of hits the edge of the ocean, that's fine. You won't be penalized for that. But what we are looking for is a random starting position and a random angular and linear velocity, which will lead to different kinds and variety of figure eights. So you might ask, okay, what's the big deal with this randomization? And the idea is we want to ensure that the figure eight you are drawing is precise enough that you can detect when to switch from the clockwise circle to the counterclockwise circle, and so on and so forth. And that works for a range of values. So when you record your video demo, which we'll talk about later, what you have to submit, I really encourage you to run this script multiple times to convince the evaluator and the grader that indeed your choices are random. And one way of doing that is a requirement. So be careful to read everything on the slide as well, because in addition to the random figure eight being drawn, the center position of where the starting position of where the figure eight starts from, it needs to be displayed on the terminal as well. Okay, so that is like a requirement for the ROS node. So make sure you don't just draw the random figure eight and forget about displaying the center position. So I do believe we have a demo for this as well. So here we are running our random swim school. So let's wait for this to execute, and you can see how it teleported to some random point. That position is displayed here. The center position is 3.1, 3.2, and then the angular velocity and the linear velocity were randomly chosen. It looks like here they were chosen out of the range, so your code should respect the same range as before. And I've paused the video or stopped the video before it could complete the figure eight, but you should let it run. You can let the turtle continue swimming in figure eight as long as the node is not cancelled. So you don't just have to stop after one iteration of figure eight. And if you want, you can clear this line as well. You can use a Turtlesim service called clear or reset or spawn to make sure that this line doesn't appear. But if it does appear, that's no big deal. Okay, so it's not going to be counted towards any kind of evaluation. So that's 1A and 1B. Both are these figure eight problems, one with randomization and one more sort of intentional and user defined. So let's keep going. We have two more problems that you have to submit. The next one is a problem called back to square one.python. So you have to write this node, of course, as with the previous cases. So what do you have to demo here? So upon running this ROS node back underscore 2 underscore square underscore 1 dot py, again, you will query the user to input the length of what will become the side of the square. Okay, so in a nutshell, you have to ask the user to input a number between 1 and 5, and any number, including floating points, is allowed. And whatever this number is, after you hit the return key, a few things have to happen. First is the color of the ocean will become red. Okay, and you should again look at some, the color topics of Turtlesim that we haven't covered in the lab, but they existed. We mostly focused on the command velocity and the pose, and you may even want to look at some services in Turtlesim that can help you with this. But what should happen is you get the input, a number between 1 and 5, you hit return, the ocean instantly turns red, and a square is drawn with the length of the side of the square equal to the number that the user has input. Okay, so a very, very important point I want to emphasize. We want to see the turtle swim and draw the square. In Turtlesim, there is a service called teleport relative and teleport absolute that you should explore for this problem. But we don't want the turtle to just teleport from one point to the other. And so teleporting means it's an instantaneous jump. So that is not what this problem is asking you to do. What you need to do is have the turtle swim across each length or each edge and draw a perfect square. And that's really what you have to submit. To ensure that your square is always within the ocean itself, you have to also force the bottom left corner of the square to always be at 1,1 in the ocean. So again, pay attention to all the requirements. The ocean must be red. The turtle must swim to draw the square. I'll show you that in the demo. And then it should also have a fixed starting point, which is the bottom left corner. It should be 1,1. That's where the square needs to be drawn from. In this case, again, if you want, you can allow the turtle to keep swimming in the square as long as the node executes, or if you want, you can stop the execution even after one square is drawn. Either is fine for this problem. For the figure 8 problem, I really want you to keep the turtle swimming. So let's take a quick look at what back to square one would look like. And what we are looking for is, again, we run this and it will prompt me for a value. So enter the square size and I enter some size. And then you can see it moves to 1,1. The ocean turns red and the turtle is swimming. It's not teleporting. It's swimming from each vertex to vertex. And then in this case, again, I exit after the square is drawn, but it's up to you if you wanted to continue tracing the same square. So that's what you have to submit in your assignment, this ROS node that will accomplish pretty much what was shown in this demonstration. So as you can see, we're progressively, building upon some concepts and making our turtle excel in our swim school. So that was all of problem 1. It has 3 subparts, 1A, 1B, and 1C, and we already covered what you have to submit in each. The second problem is called swim to goal. And the idea here is you have to write a node called swim2goal.python, and then it has to you have to demo the following abilities. When you execute this ROS node, it will prompt the user to enter a x coordinate, which is the x coordinate for the goal. I'll explain why I'm calling it a goal right now. So you can spawn the turtle in the center of the ocean with a fresh Turtlesim instance, and it will spawn in 5,5. So the user has to input the x coordinate for the goal. Example is, let's say the user says, I want you to go to the x coordinate of 1. Similarly, the user will input the y coordinate for the goal. So in this case, our goal is 1,1 and maybe our turtle is at 5,5. Then the user will also input something called a tolerance value. And I'll explain what is meant by the tolerance. The tolerance in a nutshell is when do you realize that if you are within a radius around the goal where the sorry, if you are within like a ball or a circle around the goal where the radius of that circle is the tolerance, right? So that's how you can visually figure out what tolerance is. So you have to get three inputs from the user: x, y, for the goal, and the tolerance that you want your Turtlesim to respect. And when you hit return, the turtle should again swim, not teleport. It should swim to the goal. But here's the kicker or a twist. In this case, it's not just swimming in a straight line to the goal. As it is swimming to the goal, the linear velocity and the angular velocity are a function of the distance between the turtle's pose at any given time and the goal itself. Okay, so this is like a proportional control, if you are familiar with that. But if you are not, that doesn't matter, because I'm going to explain what this means. So we want the linear velocity in all previous examples was a fixed velocity, right? So it's 3.1 or whatever the user inputs. Same for the angular velocity. In this problem, you're not getting any velocity information from the user. You're only getting a goal, and you compute the velocity at every decision point or every time step where the velocity is proportional to how further away you are from the goal. Meaning the further away you are, the faster you are, and as you get closer to the goal, you become slower and slower so that you can reach the goal within some tolerance. Okay, so I'll show you again what this looks like. And in this problem, we are also asking you to display the RQT graph for this entire system, swim to goal system. And you have to add a little bit of an explanation on what topics you are using and what, how the command velocity is getting computed and things like that. Okay, this was not a video, but here's what your execution would look like. The user enters the x, y, and the goal. No, not and the goal. The xy is the goal and a tolerance value. So you can see on the screen, in our example, our turtle is in the middle of the ocean, and we say we want you to go to 1,1 with a tolerance of 0.1. And then the turtle swims to 1,1, but you can see how it's swimming in this arc. The reason is because it's not using a fixed angular velocity or a fixed linear velocity. It is both these velocity components are changing based on how further away you are from the goal itself. Okay, so what does this proportionality mean? I'm giving you a few hints that you can literally use in your code. You can think of the x component of the velocity as some multiplier times the Euclidean distance between the position of the turtle at any time and the goal itself. So we know that the goal is already known to us because it was given by the user, but you have to subscribe to the position or the pose of the turtle, compute the distance, the Euclidean distance between where the turtle is and the goal, use that value and use some multiplier. In this case, I'm using 1.5, and that becomes the linear velocity. And similarly, for the angular velocity, you want to compute the arctangent of the y component of the remaining distance and the x component of the remaining distance, because this function a_tan2, I think it requires two input arguments. So you can, instead of the distance, you can split that into the y and the x component, use that as the inputs to compute this arctangent, which is again, a function or proportional to the remaining distance, and again multiply it by some reasonable value and use that as the angular velocity. So proportional speed and turning means that the rate of x velocity and angular z velocity are proportional to the remaining distance, and you can use sort of this hint that is displayed here. You can use the same components, but it's not required. You can change them as you see fit as well. What we are looking for is that the turtle, swims to the goal with this curve, and we can see how the angular rate and the linear rate are proportional to the distance. So this is really what you have to submit. a quick kind of word on tolerance. So tolerance is really, like I said, the radius or this constant which dictates how close the turtle needs to be to the user goal before we can consider that it has reached the goal. Because remember that the pose of the turtle is some floating point value, and the user's goal maybe is 1 comma 1 in this case. So what if my turtle is at 1.0005 comma 0.9998? So it's not exactly 1 comma 1, but it's out and about the goal, and so that's what tolerance is asking you. So clearly, if your tolerance is too large, you have more slack, but you cannot make the tolerance super large as well. So a good value of the tolerance is between 0.1 and 1, and that's sort of what we expect to see when you run your code. So don't use a value of tolerance which is greater than 1. So like I said, tolerance is needed, as the slide says, because the pose of the turtle is a floating point value. And one thing that will be super useful as you write this ROS node is to round all the information to some kind of exact number of significant digits or decimal places. So you can say whatever the pose I get, I will always round it down to only one place of decimal or 2 places of decimal. And I think that will be a very good, you should make good use of this Python command, because it will be very useful to figure out if you've actually reached the goal, and even to compute your linear and angular rates. So I hope this is clear as well, what swim to goal ought to do. And again, for problem 2, here are some useful declarations that you might consider adding to your ROS node. Some of them are already known to you. So geometry message twist, Turtlesim pose, ROS pi, and because you have to compute this proportionality stuff and Euclidean distances, you may want to import power, a tan 2, and square root. Okay, so those are the 4 problems. Really, there are 2 problems. The first one has 3 parts. And now the big question, okay, so what do you have to actually submit for this assignment? So let's go over this one thing at a time, because there's a lot to discuss. First of all the ROS nodes that you are creating should reside in the AutoTurtle scripts subdirectory inside your Catkin workspace. Okay, so this is the same directory where the template code is already provided. And so you just need to add more ROS nodes to the same directory. Then what you should do is, after you are convinced and happy with your demos for each problem, you need to compress your entire AutoTurtle folder. So not just the scripts folder, I need the entire package, the entire AutoTurtle folder. Again, don't submit your entire Catkin workspace, okay? So workspace has beginner tutorial as another package as well. We don't need all of that. We just need your AutoTurtle folder in which you have added your new scripts. You just need to compress that into zip format. Rename this compressed file to your computing id.zip, and then upload it on Colab. And so the submission will be open on Colab, and you, if you're registered for the course, you have access to Colab. And so you should just upload a single file for your submission. Don't upload each script file individually and package XML. We really just need the zip file of your AutoTurtle folder. It's pretty straightforward. So just make sure you upload as advised. Before upload, it would be a good idea to make sure that if you run a Catkin make on the workspace which has the AutoTurtle folder, doesn't throw any errors in your AutoTurtle scripts. Because internally we will have to run Catkin make when we download and unzip the submission. And if we see that the AutoTurtle package is throwing errors and it doesn't build or compile, then we won't be able to give you any credit, because at least for the code part, because we aren't able to run your code. So to ensure that both your code runs, do that as well. But in addition, you actually have to submit a video of all the demos as well. Very similar to how I just showed these small little clips of these nodes executing and the output. You have to do a video submission. So let's talk about what that looks like. So you need to essentially record the demo for each problem that you submit, and you can use any screen recording software. I do believe in Ubuntu there are free software such as Record My Desktop, which will just record the entire screen, or you can use OBS, or even if you have some other screen capture software, feel free to use anything you want. But what we want is not like 4 different videos, one for each problem. You need to just upload one video which has all 4 demos. So I leave it up to you whether you want to just do everything in one take, or you want to record individual demos and stitch them up later in some software as well. That's also fine. Really doesn't matter. But as long as we get a single video demonstration, and that's what we want. What do you actually demo is running your node, and each problem has the list of what has to be demoed, what you have to show, and so that's really what your video submission should look like. In addition to that, you should include, so you don't have to upload your video. Remember, the only thing you have to upload is a zip file. So how do you share your video is the next question. So you should include a PDF file also in your zip file. So it doesn't just have the AutoTurtle folder, it also has a PDF file. And that file contains a link to where the instructors and the TAs can view your video. So you can upload it to Dropbox or Google Drive, or just easiest for me is to just upload it to YouTube, and you can unlist it if you're worried that others will see your demo, and although just visually seeing the demo doesn't help because I've already shown you the outputs. So you can even make it public, and that's completely fine. But we need a link. We need a link where we can go and look at the video demonstration, because we will evaluate how good your code is also by looking at the demonstration. In addition, if you recall, in one of the problems, I asked you that you have to include or show the RQT plot. You can even screenshot the RQT plot, put it in the PDF, and discuss how it works for problem 2, I believe it was. So the summary of what you have to do for submission is we need the entire AutoTurtle package plus a PDF file which contains the link to the video demonstration, but it needs to be just one video, right? So don't submit a separate link for each of the demos. So that's really what you have to upload as far as the submission is concerned. All of this submission is on Colab. What we will do on our end, just so that you know, is we will unzip the AutoTurtle package. We will obviously view the videos that you have included the link to in the PDF, and then we will run your code with the following commands. Okay, so we'll run each of the nodes with this exact name and see whether the input is correct. All right, so almost there. There's just one more piece that for each problem of the assignment, so we have 4 problems, 1A, 1B, 1C, and problem 2. For each problem, you can earn 10 more points if you also submit a launch file that will launch all of the things required for that particular problem. So for example, for back to square one, your launch file should be such that it launches Turtlesim, and then it also launches your back to square one node, all in the same launch file. Okay, so if you create other nodes or whatever nodes you create, if you can provide, and even during your video demo, show that to run that assignment sub problem, you are using a launch file and not running raw score first, then opening Turtlesim, then running the node on its own, then that's the way to demonstrate that you have successfully also written a launch file. So maybe that was confusing. Let me rephrase what I mean by this. For each problem, so swim school, random swim school, back to square one, and go to goal or swim to goal, you can add a launch file or write a launch file. And in your video demo, you can show that rather than launching each node separately, you are just using your launch file and everything is getting launched in the correct order on its own. Okay, so that's what I mean by the evidence that your launch file works is also to be included in the video demonstration that you record. In addition, the AutoTurtle package only has a script subdirectory where all the nodes reside. So if you attempt this and you have a launch file for each problem or whichever problems you have submitted, make sure those launch files are put into their own launch subdirectory. So you need to create a new subdirectory in AutoTurtle called launch, and then add the .launch files for each problem or whatever problems you have submitted to that folder, because that's where we will look for these launch files when we evaluate your code. So you get 10 additional points. I think overall, I haven't done the math to confirm this, but it looks like this entire assignment 1 is for 140 points, including these 10 points for each of the 4 problems. So yeah, so I know it looks like a very long assignment, but you will go through this pretty quickly, because once you get the swim school going, others are just incrementally building on top of that. Again, make use of Piazza to share where you are getting stuck. Don't post, don't post that, okay, debug my code, these kind of questions on Piazza. You should try to explain. We can discuss concepts about how to attempt these problems rather than code debugging. So that's what I encourage you to make avail of Piazza. The TA will also announce their office hours for this assignment, so you should make avail of those office hours as well. So yeah, so this is a pretty large assignment, but like I have said before, this course doesn't have any exams, so the assignments tend to be where you earn your grade. And so this is kind of a, putting the lid on the ROS part of this module. And after this assignment, or by the time you submit, we would already be into the perception planning and control parts of this module, where we will look at going from Turtlesim now to the F1tenth ROS simulator. So that's all I wanted to cover in this assignment description. Announcements will go out on Piazza, on Colab, and I will also post a copy of this PDF along with those announcements and update this on the course webpage. So that was it for this short video on assignment 1, and I will see you in the next lecture. Yeah.